Okay, welcome back. We're gonna continue studying this model. Let me now share my screen again. Um, and now we saw the effects of heavily taxing the dirty sector. Okay. Um, so in subsection 183, we are taxing the dirty sector and not taxing the green sector. And here we see some effects, some more sizable effects in terms of the decrease in dirty output and increase in the green output. Then we take this to another extreme by taxing the dirty sector at 70%. That's a huge tax rate. And then subsidize the green sector at a very large subsidy rate, right? Because if I set the tax rate negative, right, this becomes a subsidy in this particular context. So now I am promoting the production of the green good because I am decreasing the average cost faced by the green firm, and I am increasing still the average cost faced by the dirty firm. And now I see a huge increase in the price of dirty output, right? Because now, remember in the very beginning, without taxation, the price was equal to 0.6, price of dirty goods. So here, of course, what we care is PD divided by PG, right? Because we normalize the price of the green good to 1. Now, at this extreme case, where heavily taxing the dirty sector and heavily subsidizing the green sector, now we see the largest effect on the price of the dirty good. It is now very expensive. And we see a comparatively larger decrease in the dirty output. There's a comparatively large decrease in the dirty output, okay? But whatever we do, and of course here, since I created an even larger distortion by taxation, utility gets even lower. Okay, again, there is no reason that requires the government involvement because we didn't put the externality, negative externality to the utility function yet. Okay, so we have these results. Now, one problem, of course, is this productivity difference. Okay, so green technology is not very productive. In fact, dirty technology is 10 times more productive than the green technology. So even under heavy taxation of the dirty sector and heavy subsidization of the green sector, the economy still produces a large amount of dirty output. Okay? So one reason, as we are seeing here, is that productivity difference. Now I equate productivity levels, okay, without changing the average productivity, right? Because in the average productivity in the economy is 11, right? One firm has 2 units of data. This is the productivity level of green technology. The other firm has 20 units. So the average productivity is, this is plain average, of course, not weighted average. Just arithmetic average is equal to 11. Now I do this experiment, okay? I imagine a counterfactual case where green sector is equally productive, okay? And I shut down the taxation. Now, look at what happens. If the green sector is equally productive, then even without taxation, the price of dirty good is very large. Okay, and proportionally, the share of green output is larger. Okay, so here, for instance, if you look at the first case, look at the difference. 12 divided by 27. Here, look at the difference. 21 divided by 29. You see the difference? So productivity is important. This is why some economists argue subsidizing the scientific research in green technology. So it is not sufficient to tax the dirty sector, to put carbon taxes to punish the dirty sector. In the meantime, we have to increase the productivity of the green technologies. So green technologies, if they become more productive, then economy automatically under laissez-faire, they will switch to the green technologies. All right. So it is essential. It is imperative to focus on the productivity of green technologies, to make them cheaper, to make them more productive and more high quality. Okay, higher quality green products, etc. Okay. So that was the last experiment I did with the model without externality. All right. Now we want to introduce externality. Okay, and we're going to introduce externality in this simple way. I'm going to assume that the dirty output decreases the utility. Okay, in this quadratic way. So if it gets larger and larger, this utility the household gets increases faster. Okay, it is convex, as you see, right? This cost, utility cost, or this utility is now convex, and it is, of course, there's minus here, so gamma is positive, and gamma measures how sensitive the household's utility to the dirty output, to the environmental problems. Okay, so now the externality is there. All right, but why do we call it external? Well, because we assume that households are not going to internalize their decisions' effect on output. All right, so the household in this way, in this version, is not gonna think, okay, if I decrease my dirty consumption, then that would decrease dirty output. They don't gonna think in this way. They still want to maximize their utilities, that part, okay, without necessarily concerning themselves with the externality. Okay, so they create an externality to themselves. Of course, in a multi-agent framework, you can do this. One agent is internalizing the effect, the other agent is internalizing the effect, but all of them creating externalities to others. All right, but in this simple version, with one household, this remains as an externality if the household does not internalize the effects of his or her decisions. Okay, so we still have the same equations except for utility. Okay, so let me show you the MATLAB code. So this is utility without externality, right? And this is utility with externality, right? With externality, I have gamma yd squared. Sorry. Okay. The rest is the same. Now, I have these results. Okay, if I run it without taxation, okay, without taxation, the rest is the same. Okay, but utility is now equal to 0.44881. Okay, so if you compare this with the no taxation case and no externality case, the utility decreases by about 7 utils. Okay, that's important. That's a sizable decrease. And of course, as you know, utility can be negative, right? Because here we are working with ordinal utility, right? So you know these concepts. It's not cardinal. It's ordinal. So it can be negative, and here without taxation, there is a large decrease. That's because of externality, right? Because if you take the square of yd and multiply it with gamma, that creates the decrease. Okay. Now, once again, we do taxation. Again, taxation and subsidizing the green sector. So taxation of the dirty sector and subsidizing the green sector. And look at the difference between two cases. Now, with externality, government involvement in the market increases welfare. Okay, so without taxation, the utility is minus 0.4, minus 4.48. With taxation and subsidies, the utility is minus 0.88. Okay, so on top of that, if you create an increase in the productivity of the green sector, you can also increase your welfare. So of course that becomes a dynamic model, because you spend today on green R&D, and that green sector R&D pays in the future with a higher theta G, right? But I mean, you can do experiments in a static framework by increasing theta G as well, and you can get even different results. The important part is that with externality, government involvement is necessary to increase welfare, right? Because now government is moving the economy from the third best to second best, right? First best is impossible because, I mean, in this framework, because dirty output is positive, okay? Because there's always a demand for dirty output. Why? Because utility is logarithmic, remember, okay? There's always a demand for dirty output, okay? So now we want to do the calibration exercise, okay? Now, of course, this is exactly going the reverse, right? Going the reverse direction. Why? Because now, let me just show you. So this is now some social accounting matrix. How do I write that matrix? In this way, okay? So in the first row, I have firm D. In the second row, I have firm D. In the third row, I have labor. In the fourth row, I have consumer. In the fifth row, I have government. So the first column is firm D. The second column is firm G, right? The third column is labor. The fourth column is consumer. And the last column is government. So this is this thing that you see in green is the theoretical SAM. Okay, social accounting matrix in the model. It is SAM model. All right. So I calculated using these theoretical results SAM data. Okay, as you see, SAM 1.1 is this. Okay, SAM 1.2 is this. SAM 1.3 is that, etc. Right? So remember, incomes are in rows, expenditures are in columns. For instance, firm D spends that amount for firm G, because this is the intermediate input demand of firm D purchased from firm G, right? So that becomes firm G's income and firm D's expenditure. Then labor cost is paid by firm D, so this is expenditure of firm D, and that labor cost is equal to W times LD, etc. Right? So that's the tax paid to the government, and that becomes part of government revenue from firm D. That is the government's revenue from firm G, etc. So you already know how it works, right? What I do is, for one simple experiment, so of course those numbers will be changing now. So let me go back to my PDF. Okay, we are going to do that for tax rates equal to 0.1. Okay, so I go to my code and put my tax rates back again as 0.1, and productivity is 2 and 20. Okay, so that difference is there as well, and I run it. When I run it, I obtain the results. So these results now must be consistent with my PDF, right? So 1.7, let's check, 5.82, 155. Yes, so it's correct. Okay, so this is the same equilibrium. Look at the price of the dirty good. It is 0.64, and it is 0.64. Now, of course, we're gonna assume that what we know is this data. This is data SAM. Okay, this is data SAM. So we assume that we know the data. We also know the model, right? Model is ours. And we also assume that as the government, let's say, we know the tax rates, and in the markets, we observe the price differences. Okay? So this is what we assume we know. All right? Tax rates, the price ratio, and the firm and the SAM data. Okay? So because this is our accounting, right? I go to the administrative data collection units, the Ministry of Finance, let's say, in the country. So I get the data, right? How much government collected from the firms, how much they gave to the how much the government gives to the consumer, what is the payment to the labor services, and what are the transactions between the firms. It's all in dollars. Okay, and this is the paycheck of the consumer, etc. Right? So this is the transfer. Sorry, where's the this is the transfer of the consumer, etc. Right? So I know the data, the SAM data. I know the model, but I do not know these parameters. Okay, I do not know these parameters. I do not know the input-output coefficients. I do not know the value-added technical coefficients. I do not know the productivity levels of the firms. I do not know the preferences of the consumer, and I do not know gamma. Okay? My purpose in calibration is to use what I know, basically the SAM data, SAM model, the tax rates, and the price ratio, okay, to recover these parameters. How do I know that? Can I calibrate all of them? Can I identify all of them? We're gonna see. Okay. Again, this is SAM data, and this is SAM model. Okay, the first element must be this, right? Firm D's payment to itself for its intermediate input use of its same product. That depends on value added, so that it depends on labor. Same is true for 1, 2 element, right? Firm G purchasing some of the firm D's output. Okay, so make a payment to firm D, that becomes the expenditure of firm G and income of firm D. Okay, so that goes on. So what is there? 1/4. So this is consumer's payment to firm D. This is total payment. Okay, so it is PD times CD. Okay, and that total payment must be equal to that 1 minus alpha times W plus T, right? So that goes on. I know the theory, I know the solution, right? So I wrote these things. For instance, SAM 4.3, fourth row, third column. What is that? Fourth row, third column is consumers' labor income, right? It's a spending for the labor account, and it is income for the consumer. So that income, of course, must be equal to W times LD plus LG, right? Because this is total labor supply. In equilibrium, these are equal, right? So this is equal to 1. So that's equal to wage, for instance, right? 4.5. The fourth row and the fifth column, 2.46, 2.64. What is that? That's the transfer. Government spends that amount, consumer receives that amount. So this is T, okay? And so on and so forth. Now, as I just said, in this very simple model, we can directly obtain W, okay? We can infer W from the model. Of course, in reality, there is a set of occupations. Wages are different, even for the same occupation, but for different people, wages are different, etc. So in reality, of course, that is too complicated, and you may never get a single wage rate, obviously. Maybe you can get some sort of a base wage, but you can never get a single wage rate like this. But this is the simple model, so it works. How do we know that? Again, in equilibrium, total labor supply is equal to 1. Okay. In reality, of course, it will not be equal to 1 because there will be some number of people working. We also know T, right? Because government, there is one government here and one consumer. So if government makes a transfer spending, that transfer goes directly to the household, and I look at the data in the SAM. In the SAM data, I directly observe that, right? So then T is equal to 2.64. All right. Then calibrating alpha is very simple, right? Why? Because I know the income, right? I know the income, and I know how much to spend on green goods, how much consumers spends on the green goods. I could also do this with the dirty good as well. Doesn't really matter, right? Because then I would get 1 minus alpha, and 1 minus alpha would be 0.8. Then alpha would be 0.2. Okay, so I calibrate alpha accurately. All right. How do I know that? Because it is deterministic. The model is deterministic. I solve the model with this parameter. These numbers that I now interpret as data is actually coming from the solution of the model. So when I put them back into the calibration exercise, of course, I get 0.2. Okay. Now, I also have this, right? So I also have total payment. Total payment to labor account made by the dirty firm, total payment made by the green firm to the labor account. I know these totals from the data here. Firm D spends $5.82 for labor. Firm G spends $8.7 on labor. Okay. Now I know these totals and I know the wage rate. So this is theoretical SAM. This is data SAM. Now I infer the labor market allocation, the labor allocation in the equilibrium. Okay. So are these true? Yes. If you go back to check the values of them, they are true. I can show you here. You see, LG is 0.60, LD is around 0.4. Okay. So why knowing LG and LD is important? Because from there, we're going to go to other parameters. How? Well, one thing that is important, and maybe we haven't discussed this very, explicitly in the last couple of weeks. So if you look at this row, okay, if you look at this row, this gives the total market value of the dirty output, right? So it must give you PD times YD, right? Because this is output by firm D, used by firm D. This is output by firm D, used by firm G. Of course, these are multiplied by prices. And this is the total payment of the consumer to firm D, okay? So this summation is then gives you PDYD, and this sum gives you PGYG, okay? These are total market values. Then these are equal to that. In theory SAM, in model SAM, I have these, right? Then I can use these totals to find intermediate input coefficients, input-output coefficients, okay? But you should be careful the role of PD here, right? PD must appear here, so PG is here, but it's equal to 1. So be careful with that. But if you put LG in it, so LGs are here. Okay, for instance, this is, sorry, this is price. Where LGs? Oh, okay, I don't use LG data here particularly because I already have the sum total and I already have the prices. But at the end, these ratios give us the input-output coefficients. Are they correct? Yes, they're correct. Yes, let's look at them. 0.5, 0.3, 0.2, 0.1. 0.5, 0.3, 0.2, 0.1. Okay? So once again, I accurately calibrate these things because I have the model, I have the data originating from the model. Okay? Now, we have 5 unknowns, right? We don't know VGs, we don't know VG, VD, we don't know theta G, theta D, and we don't know gamma. But the problem with gamma is this. I have no idea what gamma is equal to, right? I cannot infer what gamma could be equal to by looking at the SAM data. Why? Because I do not ask consumer how much they lose welfare when there is dirty output around, okay? And household does not internalize its effect, okay? So in the SAM data, if you look at theory SAM, if you look at that part, right? This is your model SAM. In the model SAM, you don't have gamma anywhere because again, household does not really internalize the effects of environmental degradation, dirty output, all right, carbon dioxide, etc. So since the household does not internalize that, I don't see anything about gamma here, right? So it is not possible to identify gamma in this model, all right? You may try to do survey work. You may try to, I think it is called implied preferences approach or something like that. So you can design surveys, a particular survey to recover how people care about the environment, how people care about inequality, how people care about other external stuff. Okay, externalities. I think it's called implied preferences approach, but I'm not really sure right now. But without having any data and any theory, we cannot, of course, calibrate it, right? Then we have 4 other parameters, V's and thetas. And we realize that we can only calibrate the ratios, all right? We can only know the ratio of theta to V and theta D to VD and theta G to VG, all right? Why? Well, because I have only that data. I cannot separately identify these parameters. I cannot separate value added from output, okay, without knowing V. All right, I can only look at total output, okay? I can only look at total output. Then from total output, I can only look at labor, and then I realize theta G divided by VG, for instance, or theta D divided by VD, okay? Final comment. Firm level text data does not really matter in this model. Okay, so here you have firm level text data, right? The first firm pays 1.55, the second firm pays, the green firm 1.09. So this data, is not helpful for anything because these equations are satisfied in equilibrium, okay? So you can check whether they are true, and they're true, but they do not help me identify anything. Okay, they are not informative. Okay, and you may play with the algebra a little bit to show why this is the case. Okay, so that's all. That's how do you use SAM data and SAM model in a very simple model of taxation, so that you can calibrate at least some of the structural parameters, not all of them. We cannot, as you see, separately identify V and theta, right? We can only solve for a ratio of theta divided by V with the given data, but without knowing V, we cannot have theta. Without knowing theta, we cannot have V. All right. One thing, of course, you can do in theory is to say, all right, value added is proportional directly to the output, then your V's are 1, right? VG and VD are equal to 1, then your theta is identified. Okay, now I can answer your questions. I will send the codes, by the way. I will upload the codes. So at some point you can try running these things by yourselves. Okay then. I see that you have no questions, any comments, any input. All right, great. So last week will be our last session, last lecture. We're gonna have an overview of what we have done in this semester, and then we're gonna talk briefly about the dynamic models, dynamic general equilibrium models, okay? And that will be the last chapter in our agenda, and that's it. So see you next week then.
See you.
Okay,
Hocam, geçen haftanın sorduğunuz sorunun GAMS kodunu da gönderecek misiniz?
exactly, I will do that, yes.
Thanks.
Okay, bye-bye.